Hello and welcome to another Teaching Mathematics webinar. We're joined today by Leigh. Hello, Leigh.
Hi, nice to be back.
Welcome, welcome. And today we're talking about Euclidean geometry again.
One of my favorite topics.
Oh, good. And of course we have Dylan pressing the buttons behind the scenes. Hello, Dylan.
Hello.
And also coming up with some great ideas. I remember that clearly.
That's what I do.
No pressure, Dylan.
No pressure.
Of course, if you want to talk to us, please talk to us. We get...
Lonely.
And now you're insulting Leigh.
Okay, sorry, Leigh.
Don't worry, I'll understand. But I think they should talk to you because
Yes.
it's an opportunity to ask their questions.
Yes, please talk to us. Use the hashtag MEMaths or find the post on Facebook on the Digital Classroom South Africa Facebook page and make a comment there. Dylan will be watching both feeds and
Great.
he will report back to us if you have anything that is worth reporting back. And you should. You should really, because there's one controversial thing that we're going to start the topic with.
I'm sure we are.
Yes. Today we're talking about grade 11 Euclidean geometry. Oh, I forgot to mention, if you do talk to us, you might possibly win 110 Vodacom airtime. 110 rands worth of Vodacom airtime.
That's a deal.
It is good. And if you would like to win something more, like a phone or a tablet, all you need to do is submit your favorite teaching resource for this section, which is Euclidean Geometry, to us, to the email address competitions@digitalclassroom.co.za with the secret code that will appear somewhere on the bottom of the screen at some point during the lesson. The point of Dylan's choosing. Watch out for it, write it down, then send through your favorite resource and we'll make them public. Of course,
Came
you
to
can
fame
find...
That's a good one.
Yes. You can find all of the details for these competitions on the website digitalclassroom.co.za/webinars. So go take a look. You should be watching this show from there right now. So
Great.
there we go. Okay, Leigh, we usually begin with Teach Like a Champion. The book Teach Like a Champion.
That book has really done its rounds.
Yes.
It's actually great.
And at first I was really enjoying the book and I saw a lot of merit in it, but I must be honest, the more I'm reading it, the more I'm seeing a pattern develop, which is this need to conform within a classroom and conform the education that's taking place, and everything's about conformity. And as soon as I see conformity, I want to run away, because that's not what life is it?
No, it's not. Is it written for the American
It is.
Yeah. They're very much a conformist society. They
Yeah.
do not break rules. They do not do anything unusual, not like us. We
And
don't even
yet
know the meaning of the word
they've got
rules.
25% of the world's prisoners are in America.
Yes, well, that's why they're probably in prison, but they actually get there, which is amazing. But I think it is that, I mean, if you look at them generally in terms of their behavior on the roads,
Yes.
queuing or lining as they lining up, as they said, they don't ever push in or shove in or anything like that. It's all done it's like Australians are also like that.
Okay,
So maybe that's got to do with it.
maybe. Let's take a look at the steps. The step is called Name the Steps. It's step number 13, unlucky 13. And it says, champion teachers help their students learn complex skills by breaking them down into manageable steps and often giving each step a name so that it can be easily recalled. Now, on the surface, this looks like a great tip, doesn't it?
I suppose it depends how far you're going to take it.
Yes. And with something like BODMAS, it is a really great tip because teaching order of operations is...
Essential.
Yes, and there is only one way to do order of operations. But when you start looking at other things, that maybe there are 2 or 3 ways or 5 million ways, what are we doing by teaching one set of ways?
Well, you're limiting a whole lot of children from actually understanding what you're doing, because one child will see it one way. I mean, if you look at the different styles of learning, one style is not going to suit all.
Yes.
So, yeah, I agree with you. There is a problem there.
I remember attending an extra maths lesson in Standard 7, Grade 9, where it was on Euclidean geometry, and the teacher stood there and said, doing Euclidean geometry is much like getting to the top of a hill. You can approach it from any direction. It's not so much the approach you're taking, it's getting to the end point. It's proving what you need to prove. Or
It is fair. It's a good way to put it, actually. Because there isn't one way. And that's why it's so hard to mark. And that's why most teachers don't enjoy it. I love it because it's nice to think how the children are thinking.
That's true.
It tells you a lot about your pupil, how they're capable of actually making sense of the problem.
Or not capable.
Yes,
Only
that's
able
the
to
other
follow
side of it, yes,
the
yeah.
step. And a lot of my teaching, if I'm honest, within the classroom was very much step-based. I used to boast that I could get anyone to pass maths just by using the step-based approach.
I think it is true to an extent. I think our examination system allows that.
Especially because we weight our answers. So it's the level 1 and level 2, you're definitely going to get this much percentage
That's
of level
right.
1 and level 2. You can definitely pass if you just follow steps.
I think the shock is going to be when they put some of the geometry in as level 1 and level 2.
Yes.
Which they will do. There are certainly questions that they can put there.
Well, especially if for the matric exam, it's 50 marks of 150, they would have to put
They
level 1 and 2.
Otherwise, it would just be the killer section.
The
which is not
interesting
good.
thing will be to see whether they rate proving a theorem as a level 1 question or as a level.
You know, that's a good question you've just raised, because we used to always think theory was easy marks. But for a child, it's probably the worst marks they have to do. Because they're not thinking, they're learning off by heart, they're not making sense. But we're going to discuss that later. And you're quite right, they mostly think, but now there's a nice rule that some of the examiners are using. After they've asked the question, they see how the children do. And depending on the performance of the children, they then categorize the questions. So say they gave a theory question and there was an 70% average, well, then they would think it's a level 1.
Yes.
But if they gave the question and they got 30% average, then they'd say definitely 3 or 4. So that's the nice thing, is they are open to change in terms of what level we're on.
That's a very interesting point.
It's a very nice way to do it.
Yeah.
It's come through with 1 or 2 of our examiners in the IEB. That's
Yeah.
how they do it.
Okay.
Interesting.
Well, you were here 2 weeks ago.
Yes. Feels like I was here the other day.
Yes. And so a lot of your points for the 5-point teaching strategy and the 3 pressure points and your tips and tricks are very similar. So we're just going to read through them quickly.
Sure.
If you would like more details on these, you must go back and watch the show from 2 weeks ago. There's even a blog post so you can read about it and my personal impressions and all sorts of things like that. But we really want to get to the nitty-gritty today, don't we?
I think what's important is to understand that things don't change. The content might change, but the approach is not going to change.
Yes.
So that's why you can go back and look at the grade 12 and get as much benefit as you can for all levels of geometry.
That is a very good point to make. You should approach the Euclidean geometry in a consistent manner throughout the grades.
I think it reassures the children.
Yes.
Makes them
That's
realize.
the beauty of mathematics.
Yeah.
It's always the same. It's just so consistent. Teenagers can feel safe in your class.
I know someone used to say to me always, remember, Leigh, life's not a maths problem. I had disagreed, but anyhow.
Such pessimism. Okay, let's read through the 5-point teaching strategy. The first one says, make sure the necessary basics are in place so that they don't hinder or do not hinder the learning. Explain the theorem in a visual and numeric fashion. Work numerically with the theorem. Move towards abstract problems. Now prove the theorem with formality. And we said 2 weeks ago that, well, why don't you recap quickly?
Well,
the
basically what I
difference?
said with the formality was actually with rigor, and it was a confusing term. I thought about it afterwards, and I thought formality is perhaps a better way, because we want the formalness of a statement and a reason and logical growth in understanding. So, yeah, for me that was it. And really in a nutshell, what I was saying with the 5 points here is that if you tackle it numerically, they can get the feel of it. So by the time they move to the abstraction, it's that much easier. And
So numerically would be where there are actual values for
Correct.
the angles filled in.
yes, you could even take it as far as a construction and make sense of it,
Okay.
but that would be quite hard with the time limit. That would be more for your junior grades, because you've got more time to do
So they would
constructions.
draw their own construction.
Yes, so in the good old days, I won't mention when, we used to have to draw our own pictures to solve our problems. And then they discovered it was actually really hard work to mark, because everybody had drawn them slightly differently. Not that
Yes.
it made a difference, but it was hard to mark because I'd labelled it differently, or whatever the case may be, to the next door neighbour. And so they had to work through, and it was just too time consuming. And then they went
Now,
towards the picture.
when Jacques was here for the grade 10 Euclidean Geometry, he said that learners aren't actually going to understand what they're doing unless they can construct in a 60-degree angle without the use of a protractor. They need to know how to do all those constructions.
Look, I don't think constructing 60 degrees would be so important for me, but understanding how to drop a perpendicular, what that means, and what it actually produces, for example, would be a great one. Or understanding that a triangle has to have certain qualities. Like I watched someone teach a lesson who was teaching Pythagoras, and they drew a triangle on the board where the hypotenuse was shorter than the two sides.
Oh, no.
Oh, I know. I nearly fell clean off the chair watching the lesson. I had to control myself because the children were getting confused, and eventually I sort of like helped the teacher along. But it actually is a problem because they've never constructed a triangle, so they don't understand that the side opposite the biggest angle must be the biggest side. So that's the kind of understanding that I would want from a construction.
Okay.
So that's where I would need it more than, say, drawing a 60-degree angle, although it is useful to know those things. For me, it's more important they know that you can't construct a triangle where the biggest angle is opposite the smallest side. It's not going to work. Or the ambiguous case for trigonometry, when you start talking about obtuse angle triangles and acute angle triangles, if you're given certain measurements. So you would have to understand that. So I do agree with Jacques. There is a real value in that.
But really, those kinds of constructions should be done in lower grades.
Yes, you don't have time in the grade 11 and 12. It's just too pressurized time-wise. It would be nice if you had the time, but you don't.
Yes. Okay, the 3 pressure points, which Dylan's about to put up for us, say you can either do geometry or you cannot do geometry.
When I hear that, my hair stands up, but we won't go there.
So this is a misconception amongst who?
I think teachers and pupils, because they'll hear, someone will say to them, don't worry, you can either do it or you can't. It's like maths. You hear people say, you can either do maths or you can't.
Yes.
Well, I don't believe that's true. I think you can do a certain level of maths regardless of who you are, but there is a point. And for me, the big issue around whether you can or cannot depends on your other subjects and the time impact to you. So, if you're going to spend 5 hours a day trying to get your geometry rider out, well then, it's easier to just say, okay, fine, I'll spend this much time and no more, because after 5 hours you'll probably did as much as you did in 20 minutes.
Yes.
So it's about realism rather than you can't do it.
Yes.
And it's also developing techniques that are useful. So I think to tell a child that, and of course the favorite one I always get is the parent will tell their child very proudly, I couldn't do geometry at school, so I understand. Well, the moment you've done that, you've given them permission to just park off and have a holiday. So to try and avoid those negative self-image problems that will arise from that.
Yes, I know as a parent it's difficult not to excuse things like that you see in your child that you have in yourself.
Especially when you've been traumatized by it yourself.
The next one says there are no techniques you can teach your pupils to make the section more accessible. And this is also a misconception that teachers have.
Completely, and you'll see when we get into our problem later on, I'll show you some of the techniques I show children in order to be able to access the problem, certainly on a level. Maybe not get full marks for it, but certainly get 40% for it, which is fine.
Okay, and the third one says geometry should be left to last as it is time-consuming.
Well, it can be. If you get lost on the way, it can be time-consuming. But I think part of exam technique is teaching children that if something's worth 3 marks, you're not going to spend more than 3 minutes on it. If you're spending 30 on it, clearly you've got a problem. So it's about discipline, and it's not only true for geometry, it's true for anything. No matter what they're doing, if they're like, often you'll find a child will start a question, get it wrong, cross it out, redo it. And the first attempt actually gave them the most marks.
Yes.
And I could cry for them in that case because all they've done is waste the time they could have done other things with. So I think exam technique is important here, especially with geometry.
And as teachers, we don't spend a lot of time on exam technique.
No, I think we leave it to the LO teacher or someone else to
And
see
what
to
do they know about answering maths
not
questions?
maths. They'll probably know quite a lot about general answering
yes.
of questions. But unless they are maths experts themselves, they're not going to know that.
No.
So I think it's our job, in my
Yes,
personal opinion.
I think so
Is
too.
to demonstrate it to the pupil and to show them techniques. And maybe if the whole class doesn't need it, maybe have a little subclass and help the children that need it. But mostly they all need it.
Yes.
I've very seldom met many children who don't need it.
Yes. Okay, next we're going to look at your tips and tricks.
Yes.
Now, the tips and tricks are the same slide that you had in the last one.
I know, it's quite boring here. I'm sort of sticking to the
they're
same
good
topic.
tips and tricks. But once again, if people do want to hear us discuss it more, they can go back in
Yes,
time
they can go and hear more.
and rewatch the show. It says learning theorem statements does not help pupils to use the theorems effectively. The second one says the visual pictures of the theorems help them to identify the theorems and problems. Third one, making sure the necessary background is in place to explain the theorem. Teach pupils ways to use the rigor of geometry to help solve a problem. Teaching them techniques from mathematical logic also helps them to streamline their proofs and gives them direction. And the last one, use color to draw out what you need.
Color for me is one of the most important things. And a little while ago at the CNA, you could pick up these little pencils. They were like clutch pencils. And I think you can still get them. I haven't looked of late. But they had different color. What was nice is if the drawing got really messy, they could rub it out and redo it. So what was nice was pencil. If you use crayons, it's not so easy to rub it out.
No.
So, that's something you can think about if you've got the inclination as a pupil to get yourself 3 or 4 colors. And then what I used to do is teach them that whenever it's a tangent, make it green. Whenever it's a diameter, make it blue. And when it's so I gave them like almost a color code. So as soon as they saw the green or as soon as they saw the blue, they knew which thing they were looking at.
I'm sure there's some sort of association then that's drawn
Yes.
with the color and the certain kinds of problems.
Well, when you teach them in grade 1 and 2, and I must admit that was an area I've just learned to know a little bit about, they use color a lot in association with shape and everything. So yes, there is a strong relationship there. Our grade 1 colleagues know some things we don't.
They are just incredible teachers. I mean, the fact that
Sure.
they can get them to read in 1 year is amazing.
It is amazing, actually.
Okay, we're going to take a look at the CAPS document.
Yep.
And we're going to get Dylan to click through it quite quickly, just to show us what's happening in the grand scheme of things. And basically what we've done is we've taken Euclidean Geometry in grade 10, put grade 11 Euclidean Geometry below it, and then below that. Dylan, could you click through the slides for us, please? Thank you. The next one. Okay, so that is the front section where it does a basic breakdown of what's happening in each grade.
Basic is the operative word. It doesn't spell out any details, so you really have to go into your CAPS document a bit more.
Yes, because when you go into the grade 11 section, which is the middle column over there, you see that actually spans over 3 pages, whereas the grade 12, where it looks like it has the most content, it has half a page dedicated to it.
Yeah.
In
fact, the grade 12 is very badly put out, I think. The grade 11 is nicely done. And the grade 10, but not the grade 12. It's too vague. It needs more detail.
Yes. Well, let's go to the next slide where we can see what's taught in grade 10. And the next is, so you see it's just basically telling you what you need to revise. Grade 11 is the next 3 slides, or are the next 3 slides. This one, that one. And, of course, it's got the examples of questions.
Yes, and the levels, which are very useful to know, because now you know when you set a problem that this kind of question would fall in this category. So that is useful. But just remember, that's not the only thing they can teach you on that. They're just giving you examples so you can see the levels.
Yes.
So they might do Theorem 1 on a low level, but you could do it on a high level too. So
and of course, if you need to brush up on what your levels are, go to the back of the CAPS document where they've said level 1 is knowledge, level 2 is routine, level 3 complex, and level 4 problem solving. Nailed it.
I know that backwards, boy. Check papers all the time.
It's easy to say that now, Leigh, now that I've given you the answer. But
of course, that does help.
Okay, but we're going to go 2 slides back where it tells us the theorems that we do in grade 11.
That's
and the
right.
reason we're going 2 slides back Yes, Dylan, that's the correct one. If you could show it on screen. Thank you. That is because we could either teach this as a checklist where we provide all of the theorems on a printed out sheet. It's very easy to do that, isn't it?
It's very tempting when you're under time pressure. But I really think we've got to be very careful. I mean, it's not many marks, but if they're going to consider that easy marks, you don't want the children to lose it.
Yes. And this is taught over 3 weeks for
3 weeks,
40 marks.
40 marks. So it's pretty
out of
much
150.
40 out of 150 instead of 50 out of 150 like the matric. But if you think of the volume of grade 11 theorems you're doing, it's considerable, but 3 weeks, again, very mean for all that work.
Yes.
Yeah, it's again, you have to watch yourself. You're better off than you were on the matric level work, but still tight.
And of course, you have to teach it to them well enough so that you don't have to reteach it in grade 12 when you only have 2 weeks.
Definitely do not want to reteach it, that's for sure.
Yeah.
I think that's fatal if you try and do that.
Now, you're going to show us how you would.
Yes.
And this doesn't mean that it's the only way to teach it.
No, it
but
definitely
this
is not.
Lee's recommendation.
Yeah, my recommendation is a little bit different because what I find is when we teach theory, and especially if we just hand them the theorem and say learn, they don't internalize what is required for the problem.
So they don't take it in and make it their
they
own.
learn it off by heart, and they say, okay, I see there's a circle, and this is A, B, C, and I drop a perpendicular to P, and okay, then this, and they don't actually come to terms, they just learn off by heart. So what I do as the examiner, I come along and I decide to be mean.
Okay, so you're drawing a circle?
So I draw a circle, and I put it at a different angle to what the textbook would give them, and instead of using the normal letters,
It's funny how letters throw them.
it does. So if they've learned it off by heart, what you'll find them doing is they'll do the theorem using the letters of the original theorem.
Yes.
Now, the problem is it depends on the marker. The marker might say, you know what, let's just let it go. But then that would be a concession over all of them. On the other hand, they might say, I'm sorry, I asked you P, Q, R, S, and you've given me A, B, C, D. Sorry, no marks. So what I would suggest, Dylan looked quite horrified there.
Quite nasty.
It is. It just depends. You know, I don't know how strict they're going to be on the marking at the end of this year. It's our first year of geometry coming back.
Yes.
And I've known cases where they've penalized them like 2 marks out of the 5 for putting other letters. So, I mean, you know, okay, that gives them 3. So 3 out of 5, not that bad. But what I find works well for me is because I teach them with picture form.
Yes.
You'll see later on, we'll discuss that. I give them a picture like this and they know this picture. And I don't know if you're in a while, you probably won't know if you haven't listened to the previous one. I'm a great believer in turning drawings around and looking at them from different angles. So if they've done that, then they're not scared by the fact that I've whipped this up into another position.
So what you're saying is that the student should pick it up and twist it around, maybe look at it backwards.
Different angles.
All sorts of things.
So if that throws them, they just turn their piece of paper around so it's facing the correct way and then work with it. Correct being the way they've been taught. Not necessarily correct as any other sense. So then what I would teach them is I would teach them what construction is required and what principle I'm going to use for the proof.
Unfortunately,
I
I'm
must
going to
write
have
bigger.
to ask you to
Yeah,
write
I do this
bigger.
always. It's called old
But
age.
it was very neat handwriting.
Good. I'm glad there was something going for it. Okay, so what I would teach them in this is not to learn off by heart.
Okay.
I'd say to them, right, the construction we need is to join the radii. Plural for radius, if you're a good
Okay.
Latin student, but it's fine. And the proof is congruency using right angle, hypotenuse, side. And that's all I would teach them.
Okay.
So what they would do now is they would use that principle, and it doesn't matter how I've drawn it or what letters I've put on it, because they've got the technique required. So the construction is to join the radii. So they would go and
So
plop
all
that
they're
in.
learning then are 3 points. They're
Correct.
learning join the radii, congruency, and RHS.
What's reason for congruency we're using, so that they can sort of prompt themselves. So there's my construction going in. And of course now they would write that up properly. So they would say join PQ and PR. but they haven't had to learn those words off by heart. They haven't been associating that with O because the O is always the center. They're now not going to be thrown by a P sitting there. Then in terms of the congruency, they would know that there are two triangles there. And if we're proving congruency, we have to find a right angle, hypotenuse, and a side.
And then they can do
So now they can do it. Well, they know that was given. There's the right angle. They know there's a shared side.
Mm-hmm.
And they would know that radius equals that radius, and that's opposite the right angle, so it's the hypotenuse. They'd write it up and they'd have it proved. Then it would just be a matter of concluding the theorem. So just so I can show you what I'm on about, let's just jot that down. I'll write nice and big. So they would say in triangle PQS and triangle PSR, we need 3 facts. The first fact is PS equals PS common. I better write bigger. I can see I'm getting smaller. We can say that PQ equals PR, and that's radii. And we can say, and we better number these, otherwise it's going to be a bit confusing, S1 equals S2 equals 90 degrees given. And therefore, triangle PQS is congruent to triangle PRS, reason right angle hypotenuse side. So that's been pretty painless up to now. So what was the theorem asking you to do? It was asking you to prove this equal to this. Well, therefore, from the congruency, QS equals SR.
Okay.
So you see how painless it is if you do it like that.
So in terms of a teaching strategy, you would, for each of those theorems,
Correct.
Give them, rather than giving this proof to learn,
Yes.
give them what they need to do.
And I would encourage them to go and do it with different letters. I'd say them, go home today and call your thing MNQ.
I suppose it's like telling someone to go to the shop versus giving them directions to the shop.
Yes, I suppose it is.
Where the directions then become the focus rather than the shop becoming the focus.
Focus, yes. I just think for me it makes more sense. It certainly made my life easier when I started to teach it, because the children related to this more.
Yes.
So like when you're doing the angle at the center twice the angle at the circumference, that theorem, then you're using exterior angle, isosceles triangle, and that's it. That's all they've got to remember, and the construction, which is the line from the point on the circumference through the center.
So it takes time from the teacher then to
Yes.
sit down and analyze what skills are needed in each
Yeah,
one.
it does. You have to go through the theorems and make sure you can give them this like 3 or 4 points, or not even 4, it's always 3, not more than that, on how to get this theorem proved in the easiest, simplest way.
Okay, Dylan, can we please go back to the slide that says the 5, don't erase yet.
Don't erase, okay.
The 5 teaching,
Tips and tricks.
the 5 teaching strategy.
That one
There
there.
we go, 5-point teaching strategy. Where would teaching this theorem fit into the 5-point teaching
Well, you definitely make
strategy?
sure that they understand congruency. So it would be necessary for them to have that knowledge of proving congruency, because you've got to make the necessary basics are in place. So you would need to know that really well. You'd have to know how to do congruency.
Okay.
Then you would explain the theorem in a visual and a numeric fashion. This is not that, because this is now the abstract. Remember in the last session I talked about don't prove the theorems till after doing the problems.
Okay.
So to give them the facts, let them work with it, but only prove it when they're familiar with it.
Okay.
I personally, I for a long time used to prove the theorems first, and they used to be lost in 5 seconds.
Yes.
So I would not start with this. What I would start with is probably a drawing where I show them, if you've got a perpendicular, then this happens. Okay, let's give you some values, and basically it comes down to using Pythagoras to solve these out. I would do a whole lot of numeric ones and say, okay, now let's prove it. So really it would fall in
2.5.
more. Now prove the theorem with formality.
So this
This
is
is the
really
formality.
last step.
Correct.
Okay. And just
Look, it
to
could be your first
clarify-
step if you believe it's better to prove them first, but I don't.
In your last, or in our last show together, you did say that you had been teaching it like that for ages.
I
and
had.
what you found with doing this last is that they understood it.
Much better. And a lot of teachers are changing to this. So it seems to be becoming popular opinion amongst teachers that it's better to teach the theory last. It sounds like back to front. I think Dylan even remarked that he was amazed by that because he himself had been dragged through all the theorems before
Yes.
you'd used them. It's very much depends on what kind of learner you are. You know, some people like the rigor and the formality of the proof before you go there. But I think for the general child population, it's easier to get familiar with it and say, okay, well, proving it's not a big deal. Look, it was 3 steps and there we go. But I know how to use it, which is more important. Because the 5 marks that are come from theory, there are 35 that are going to come for actual work.
Yes.
So really our stress should be on the actual working with our problems.
So with doing this problem over here, the numeric would be having values for the radii and...
Yeah,
or
let me show you an example of what I mean by numeric.
Okay.
Sorry, my voice is fading on me here. Does this periodically. For example, something like this would be a numeric. I would give him something like this, and I would say, okay, I know this is a right angle OABC. And I'd say, tell them that AB is equal to 8 centimeters.
Okay, so that's the chord.
Yes,
This
and I
equals
would
to 8
say the
centimeters.
radius of the circle is 5 centimeters.
Okay.
And I'd ask them to find or solve for OC. So what I would expect them to do then is to look at it and say, there's my right angle. From my theorems, I know that that will equal that. But they told me this entire length is 8 centimeters. So that means this must be 4 centimeters, and that must be 4 centimeters.
Yes.
Then, obviously, we can do nothing unless we get a radius in here. Because they told me the radius. And I wouldn't put both in, I'd only put one in, because putting in both just makes the drawing look cluttered. So I'd say, right, the radius is 5 centimeters. And they want me to find that. How do I do that? It's Pythagoras.
Okay. So then that would be the numeric.
Numerical.
And the visual would be having the drawing.
The ability to look. The abstract would be a little different. The abstract would be something like this. And I'm sure many teachers have seen, and mind you, it's been out for a while, so maybe not. It would tell you something like this. It would tell you that we've got a picture like this. This is 2. Let's just get some letters in here. And they'd ask you for OC.
Okay. And OC is from here to
there. Now, it's very vague, really. I mean, okay, they can also tell you AB. So they can say AB is, let's make it 8 centimeters, since I know that works nicely. So, right, we know it's a right angle. We know it'll bisect, so this will be 4 and 4. And this is where the abstract comes in. Because we don't know the radius, we need to realize that that's your radius, but then so is OD.
Okay.
Now, if that's the radius, this must be radius minus 2.
Okay.
And you would then use your Pythagoras on that to solve for R.
And after you've done problems like that, then you prove the theorem.
Prove the theorem.
Okay.
So that's just a small example of where the 2 levels are of the question. We didn't get to that last time, so I'm glad you asked that. It's a good question.
It's good to clarify everything. I also suddenly thought you were telling us to do the opposite of what...
Oh, no,
you
shame.
said
I
last
must be careful. See, my mind is very clear from last week still. Obviously, I haven't forgotten it yet. So, well, I don't know about obviously, but yeah. So that is my idea of it, and you'll see when I do the problem just
Yes.
now. That problem has got a numerical aspect to it and an abstract aspect to it.
Okay.
So you will see both of those come out again. But that's what I'm meaning by your... And, of course, your abstract might even be more formal than that. But, yeah, that's an idea.
Dylan, do you have a question?
I have a question.
Yes.
So looking at your list here, 3, 4, and 5, would you say that actually we're working from the most concrete to the least
Correct.
concrete? So the numerical problem is the most concrete. You could draw it out to scale even
Yes,
and
you
measure
could.
it. Then you start to bring a little bit of abstraction into it.
Yeah,
And finally, the proof of the theorem is completely abstract
That's
because
right.
it would suit any set of numbers you
That's
ever chose to give
beautifully
it.
summarized, and that's exactly what I'm meaning. And in fact, it ties in with Singapore style of teaching. They're very big in concrete, then they go to pictorial, and finally to abstract. In high school, they go pictorial abstract. They sort of miss the concrete, but not always. I've seen in the high schools they do bring in concrete apparatus as well. So you're quite right. That's exactly what you're doing. I think I mentioned last time that they're big into concept before procedure.
Yes.
And I think it makes all the difference if you've enforced that concept. The concept before you hit the procedure. Otherwise, they're just doing rote work without any understanding.
Well, it's name the steps, isn't it?
Yes, it is. It is.
Yeah.
That's
and
correct.
if you teach steps before you teach, or before concept is attained, it's...
Well, that's where
will
it falls
concept
down.
ever be attained? If
Well,
they know how to
sometimes
do
it
it
does.
without understanding it,
Do you
will
know,
they
in
ever
the
understand?
many days gone by when I was at school, they used to believe that if you practiced enough, so in other words, if you did 65 of the same thing, the concept would hit you between the eyes. And yes, that was partly true for mathematically able people. But for those less able, they struggled. It wasn't so hitting them between the eyes. There is something called incubation time, which is a very big, well-researched aspect in maths education.
It's a fascinating thing.
Very fascinating. When I did my master's, I looked at that as one of the factors. And in fact, what will happen to me is I used to often love the challenge of children bringing me questions they'd found from only the Lord knows where. And they'd bring it to me and I'd look at it fresh, first time with them, and sort of put myself under a bit of pressure. It was a bit of interesting excitement for me. I know I've got to get a laugh. But then what we used to do is I'd say to them, if you get a problem, and I think this is good to role model to children, and you get stuck, leave it, go and make yourself a cup of tea, do something, do some other homework, whatever it might be, just distract yourself a bit and then come back. And during that time, your brain has already thought it through.
Yes.
And you're that much more able to handle it. And I'm sure teachers know from experience when they're prepping. Sometimes you look at a problem and think, yo, how do you even do this?
What is going on?
And then suddenly it'll just hit you. And I found I was very young in matric. I was 15 in my matric year, which was pretty unusual even in those days, as I say, many years ago. And it used to take me sometimes 24 hours for the penny to fall. And of course that was reinforced by the teacher saying, if you do 50 of these, you'll get it. So, and I would suddenly be sitting at home, is that what he was on about? It would just hit me. So, it is partly true, it does work, but it isn't a foolproof method.
There's a saying that I've adopted recently, which is sunrise, new eyes. And it does that time away from something and then going back to it the next day.
It's a nice saying.
Whatever
like
it is, it's good, isn't it?
It's an excellent
it rhymes
one.
as well.
Because even when you're having issues or problems or something, if you just go to bed and then wake up the next morning, it doesn't look so bad.
Yes.
You're quite right. That's a very good saying. I like that.
Okay, now you supplied us with a cheat sheet, which is handwritten.
Yes, sorry for that, but it is the much easier way of doing it. And also that's how I would like my children to produce their little cheat sheet.
And that's why I decided to keep it that way, because Leigh, this morning I did start redrawing all of those.
My word.
Sure, it's quite
It's mission.
something.
No, you don't
But
want to do that.
Then I thought, what would I rather have in my classroom? I'd rather have them drawing them. Goes back to Jacques' thing of construction.
It shouldn't be you that's doing it for them. It should be them doing it. But with your help, of course. I mean, you obviously, as I said 2 weeks ago, I said you could be like spend the first 40 minutes of geometry quickly recapping, and what you'd recap is basically that sheet. But that doesn't mean they haven't tried that before.
Yes.
So you're going through it with them just to refresh their memories on what they should know, but they should have their own one. And I think it's also quite important that they see when you're drawing, like, say, for example, 3 down and on the right-hand side, the one angle at the center, twice the angle at circumference. You can see I've deliberately drawn it so that each drawing looks slightly different.
Yes.
And, of course, there it's traditional in the sense like that one on the left-hand side of that angle at the center. That one looks just like the textbook would look with your proof.
Yes.
So in a way, maybe I should have deliberately swung it one side or the other side so that it didn't look traditional. But then, the cheat sheet's about being able to take it. So almost, if they were in matric, I would certainly spend, I don't know how long it would take to do that in class, probably 20, 30 minutes. But I would go through that with them and say, remember, this is what you learned last year. Now keep it handy.
It goes back to my thought of making a geometry toolkit, that you have a little book that you write down all your theorems or your little abbreviated reasons, things like that you keep with you from grade 9 even.
Yes, the sooner the better. I mean, you can see this starts with angles on a straight line.
Yes.
I didn't even put
That's
angles
grade
around
8,
a
I
point.
think.
Yeah, and I mean, that one I just assumed they'd know, but I'm having doubts on that.
Please.
Yes.
They must know angles around the
I
point.
don't know. I marked a paper the other day where they thought there was 180 degrees around a point. I was fascinated.
Depends how many dimensions you work in.
This is true. I mean, we could be working in another plane or something. I don't know. But anyhow, I would, for me, that would be the essential. I didn't even put the congruency on the sheet. But I would almost be tempted to remind them there are 4 cases of congruency.
Yes.
Just to remember, and I maybe even mention to them, be careful of the right-angled one, because sometimes they think it's side-angle side, and it's not. It's
No.
right-angle hypotenuse side. So I would stress that included angle story with them. So, you could make this an event. I mean, you could go through it really thoroughly with them. But hopefully they've developed it as they've gone along. But I like it on a piece of paper. I tell you why I like it on a piece of paper.
Yes.
They can keep it in the back of their books.
Okay.
So when they're doing problems, they can fish it out. And, okay, I see this one, I see this one, I see this one, and it helps them. So, I think, yes, they should have a proper book of stuff, but that's nice to have as a pull-out sheet when you're working on, say, your grade 12. Then you've got the grade 11s reminding you that this is what you should know. But, of course, it is a good idea to develop, and it also depends how you draw the sheet up. So, in other words, if you're the teacher who's going to teach your theory first,
Yes.
then you could prove a theorem, let them draw a little picture on their little sheet, and then work with it.
And the actual act of drawing drawing it is a moment where they can internalize it.
Like suddenly they'll notice if they look at that Theorem 2, the angle at the center,
Yes.
that it's different to the one where the angle's in the same segment, because there clearly doesn't have to go through the center.
Yes.
The one directly underneath it, Dylan. Yeah, that one there. Yeah, and they do get confused with that. They think for some reason those are the same, and they definitely are not. And if they've drawn it themselves, they'll feel the difference in what they're doing. They're not going to the center and then to the circumference.
Yes.
I'll also use things like, for the example, the angle at the center twice the angle at circumference. I mean, it's a ridiculous analogy, but it works really well. I'll say, imagine it's a cake, and you're cutting out the bit that is 2x as your piece of cake. You must leave the x behind. So if you take the 2x and you cut along and you pull the piece of cake out of there, the x must stay behind. If it doesn't, you've got the wrong angles.
Okay.
So even on the second drawing where it's like over on the side, if you pull your 2x out, your x is still behind.
Okay.
Because its angle at the center equals twice the angle in the alternate segment. And that gives them a less formal way of remembering. So that's why when they do the 2x at the top in the third drawing, they know that the x has got to be the one down the bottom there.
Okay.
Because they've pulled the 2x out and they've eaten most of the cake and they've left that x behind. So little things like that help them spatially, adjust to it. I mean, it is ridiculous using cake, but it works quite well.
Oh, everyone loves cake.
Especially the boys.
Everyone can relate to.
Yeah, everyone wants to eat it.
Yes.
so it's a good thing. And so, they can then see that obviously that other one, the one underneath it with the angle in the same segment, that's different.
I suppose that almost speaks to the name the steps thing
Yes.
from Teach Like a Champion, where it's not
Does
so
almost.
much talking about steps, but making analogies.
Yeah, I think it's just making it more accessible is the word I'm looking for.
Okay.
So that they can look at it and see a practical way of checking they're using the right angles.
Yes.
If I pull this bit out, will my x still be there? Yes, it will. So that's cool. Then we know we're right.
Okay.
I know it's not perfect, but it's a way that's worked well for me for many years. I really enjoy teaching this section because I enjoy trying to show them techniques. I don't think I was probably not shown any of these. They're things I've developed watching other teachers, going to conferences, trying it out myself, making a mess, fixing up.
And there's a lesson in that
Yeah.
we should always be developing ourselves and developing our explanations.
Well, I was actually going to say with your book,
Yes.
not everything you read or hear is always the best thing for you.
Yes.
But there's usually quite a few points you can take from anything you're exposed to that is useful. So I always question a teacher who says to me, I don't need to go to conferences, I know how to do it. My hair just stands straight upright.
Yes.
Because even after 30-something odd years in a classroom, I still think there's stuff I can learn. There's still something new. There's still new approaches that might be better. And so, yes, I try to go to as many of these things as possible.
Yeah, and I know AMISA is very active. So
They are. There's actually a regional meeting in Gauteng, not this weekend, the 16th of August. I think it's in Attridgeville.
Okay.
But you can probably Google it. And they're discussing, I think, geometry and probability, if I remember rightly.
Really? Well, there we go. Free
so
publicity.
well worth a visit.
Go find out.
Sorry, AMISA. Sorry, mindset. But it's worth going to hear some other ideas.
Yes.
Nothing wrong with that.
No, that'll be great. Okay, we have got just over 10 minutes left,
Oh,
and you
I
do
talk
want
too
to go
much.
through
Yes, I do.
the
I do.
question, and this question has been taken from the NCS paper
Correct.
3.
Paper 3, and I think it was not last year, the year before, 2012 or 2013 at the very...
When Euclidean geometry was optional.
Yes.
Okay, we're
Before
going
it
to
became
go
compulsory.
a bit further,
on.
Dylan. Oh, sorry, just go back to that, some cheat sheets. I do have a list of cheat sheets,
Okay.
links to examples of cheat sheets that people are welcome to go and look at and use as inspiration. I will put them up on the blog. And
That
of
looks
course,
far neater than mine.
Yes. Well,
I
Leigh.
do approve. But I like my messy one.
But once again, it's really valuable drawing them yourselves.
I think so.
Okay, let's go to the next slide, which is the question.
Yeah.
Taken from the NCS paper 3, RS is a diameter of the circle with center O. Chord ST is produced to W. Chord SP produced meets the tangent RW at V, and angle R1 is equals to 50 degrees. Now, the language of a geometry question is usually the first stumbling block, isn't it?
It is, and there's a lot of waffle that they give you in the top. I mean, it sounds terrible to say that. I always used to tell my pupils that there's lots of waffle. You need to hone in on the important things.
Yes.
So as you look at that, the first thing that would absolutely smack me straight in the face is the word diameter.
Okay.
So I would immediately tell them highlight diameter.
And I think you've done that
Yes,
in the next
I will
slide.
do it in the next slide. I'll
Okay.
mention now what I'm going to do in a little while. The next word that hits me is center,
Okay.
because we've got a whole lot of theorems involving center. A chord, yes, that's important, but it could be waffly too because there are lots of chords there. But a tangent, that is very important. So this is where the colors would play a role. So straight away I would take my blue and make my diameter blue. I take my green and make my tangent green. I don't do it here. I do other things. What I do on these questions, and Dylan will flick to the next one just now, Don't worry, I wasn't disciplining you, Dylan. Dylan whipped his fingers off the keyboard immediately. But what is happening there is that I'll show you, but what I would do is before I even tackle the question, before I even look at what they're asking me, I would look at the cheat sheet and say, what pictures can I see there? And this is what you're going to see now. So Dylan, if you can whack the next one for us. Now you'll see there I've highlighted diameter and center. And you can see there I've highlighted my diameter, ROS, I think it is.
Yes.
My eyesight is improving. Maybe I ate enough carrots this week. And the center is O, and that's important. So maybe I'd make that dot thicker or something to remind myself it's the center. Because sometimes they label it with 3 letters, but it won't be the center.
Okay.
But then straight away I think, hang on, I know a theorem to do with the diameter. The diameter subtends a right angle. So even I would be tempted to fill it in on the drawing. But I'm not going to do it. I didn't do it on this for a reason, because just now we'll then use it. But if you do it as you go, well, then in actual fact your problems are usually solved by the time you get to the end of your things.
I want to pause you here quickly.
Yes, sure.
I'm in the fortunate position where I get to work with a lot of people who know a lot about mathematics. And often when we're developing resources for this kind of thing, we come to the argument or academic discussion about terminology. And it's so important that we have...
Correct.
Yes. Well, I tend to be quite diplomatic.
Unlike me. He doesn't do well on that.
One of the words that often comes up is subtends. And what does subtend actually mean?
I'm glad you mentioned that, because that's one of the things I would do when I read the words of the theorem to the children. I'd say subtend means coming from. And I would show them with my arms. I'd say, right, I'm subtending from my arms to the point P.
Like
so
this?
I'd literally do this. Say, right, my arms are subtending
Okay.
that point there. So it's coming from, this could be a chord, and there'd be subtending 2.
Okay.
So it's quite a nice thing, but there's a lovely little resource which a friend of mine introduced in the school, and we all had one. And I'm actually sorry I never brought it with me. It's basically a circle, and it's got a whole lot of nails in it.
Yes.
And you use elastic bands. And you stretch the elastic band so you can show them there's the chord, and then you can pull the elastic band and show subtends.
That's fantastic.
It's a beautiful little gimmick.
Because yes,
I'll
we
take
all
a picture
draw
of it
and
and
we
send it to you.
see
You can stick it on there.
Yes, please.
Yeah, you can actually
and a couple of
access
photos of different.
Yeah, that has the elastic band. I have to find the elastic bands because they've been in retirement, but I'll pull them out and do them. And you could use different color elastic bands. And it's really a very effective way. And you can also pass the board around. It's usually half the size of the whiteboard we've got in front of us. So it's quite, say, A3 size.
Yes.
And the hardware, or not the hardware, what we call industrial arts teacher, made them for us. So he was a maths teacher and an industrial arts teacher, a great combination. He went and he made us all these circles. He hammered in nails at so many degrees. So every 30 degrees he hammered in the nails.
Okay.
And we could have a ball with this. And the center was also a nail in there. And you could actually pull it around and stretch it and show the children was lovely.
Yes.
So I'll take some pictures of it, and then maybe they can get the the industrial arts teacher, technology now to do it. I see Dylan's having a quick look in the hope of finding one. I think they're called geometry boards, if that'll help in any way. Sorry, I'm just now making Dylan go hunting around there to find it for us.
But it is something that they could potentially make themselves, especially in grade 8.
Very easy.
They make it.
Yep, that looks like it could be it.
Something like that.
Yeah, it's sort of like, very similar to that, but it's got a circle on it.
Okay.
And that's the idea with the bands.
Okay.
So I'll actually definitely take a picture of it. I've got it at home.
Please do.
As I said, went into retirement with this geometry going out of the syllabus, but I will dig it out and find some coloured elastic bands, take a few shots and send them to you. You can post them on the site.
Yes, the blog will be.
But it's an easy thing to make.
Pictures.
Well, the industrial arts teacher did it, so I mean, I can't really comment if it's easy. But he seemed to knock up 13 copies of it relatively quickly.
Shall we go back to the question? Because we only have 6 minutes left now. And
Talk
we barely
quickly.
started.
So that's the first thing. So now if we go to the next drawing,
Yes.
you'll see there now I'm using that theorem, angles in the same segment. So we used to call it bunny ears or bow ties. I mean, there's silly names for these things, but it helps children remember them. The funniest is when they write in the reason, bow tie or bunny ears. We usually collapse with laughter, so please be careful they don't do that. It's just a gimmick to remind it. So they can see that if they're using chord TS, they subtend an angle at the top there, at P, I think it is, and one at R. Of course, you could use another chord. You could use the diameter as a chord and subtend there, but there's not one line missing there, so no. And you could play around. You could move yourself around there using different chords and seeing how many angles. So you could mark in now P1 equal to R2 with some color or something to remind you that you actually have a theorem that helps you out there. Dylan, the next one.
Wouldn't your drawing get quite busy?
It does. That's why I say it's quite nice to have pencils that rub out.
Okay.
Yeah. But, you find to manage it, it's not that bad because you'd start with the lighter colors and go darker as you go.
Yes.
So it's not so bad. Then this one here is the radius perpendicular to the tangent. And they've got a theorem that tells them that R1 and 2 equals 90 degrees. Now, that's quite useful to know. And as I mentioned 2 weeks ago, there are not so many versions of the drawing. You'll find this drawing with different questions.
Yes.
Different information. You might not be told it's a tangent, but this one you were told it was a tangent. So you have to watch out for these drawings. They occur over and over again. Sorry, Dylan, the next one, I'm being a real pain here rushing you through these things. Okay, this is tan chord theorem, which we call tan chord. So there's your tangent, RW, and you've got your little man standing at R1. He's holding on for dear life onto RT, and the angle coming off or subtending from RT is S. So there's your tan chord theorem. And again, if you turn your cheat sheet round, you'll see that picture looking at you. So you see, just by doing it, even if you didn't mark it in with color, I'm deliberately doing it with color because I think it helps you to concentrate on what's important.
Yeah.
Okay, next one, Dylan. Right, now the actual question. Notice I haven't even touched the question at this stage. All I've done is talk about it. So basically now we can look at the question. The question said, find the size of WRS. Now, WRS you already know. Earlier on, we highlighted the tangent and the radius.
Yes.
So we know that that's 90 degrees, radius perpendicular to tangent.
Okay.
First one done.
Check.
Second one says find the size of W. Now, if we know that that's a right angle, we could use the big triangle with W in it. Now, as soon as it's outside the circle, they've got to go back to their earlier geometry. So that's something I'll teach them. If it's not touching the circle, then it's more than likely angles in a triangle or
Yes.
something else like that. So it's a coping technique, if you like. So and then I'd say, well, what else can I find in the drawing? They told me that R1 is 50. Now, if R1 is 50, that means that R2 must have been 40
Yes.
because they added up to 90. But from the tan chord theorem, R1 is equal to S1 and 2. And S1 and 2 then will also be 50.
Okay.
So you've got a 90 at the tangent contact, you've got a 50 down at S, and so W must be 40. So it was a little bit more work.
It was for 2 marks.
It was for 2 marks. But, the fact that you would use the tan chord, you've already isolated that as a theorem that you're going to probably use.
Okay.
And then they ask you for P1, I think it is. And, of course, I highlighted that with the angles in the same segment. I know that P1 is exactly the same size as R2. Angles in the same segment. And R2 was 40, so therefore P1 must be 40.
Leigh, you're making this look too easy.
It is easy, I promise
But
you. I
it's not
love
hard.
it. Yeah. I think we try and make it harder than what it is because we suspect that it'll be devious. And I think when I think back to my matric here, which was many moons ago, I think I try to make the geometry harder than what it was.
Okay.
And I think that's what I learned when I started teaching, is that it isn't as bad as you think it is.
So with the highlighting with the color, analyzing the diagram before actually attempting the
Makes a
questions,
huge difference.
you are answering the questions.
You basically
before
have
you
answered
get
it.
there.
The important thing to remember, though, and this is the only danger, is if you're filling it in on your drawing, you mustn't mistake if it's something that was given.
Okay.
So, perhaps just keep that in the front of your mind to say to them, look, you can fill it in on the drawing, but remember, you put it there with a reason. It's not given. The R1, was it R1? Yes, R1 equals 50 was given.
Yes, but everything else.
But everything else was stuff you gathered using those theorems in the drawing. So the picture, the looking at a picture and identifying it, and then using the colors to pull out those theorems makes a huge difference to how you handle it. The last one is challenging. The first 3 were easy. But if you look at that, you're looking at, 6 marks at the moment out of 10. I see it's out of 15, but there must have been a theorem or something beforehand, more than
Okay.
likely. So, if you've got 6 out of 10, you've got 60% before you touch that harder question.
Now, in terms of your teaching strategy, where would you introduce problems that had multiple theorems or that made use of multiple theorems?
I think this next one here does that, I think, if I remember rightly. Because you have to prove...
But when you're teaching
when I'm
it,
teaching, right.
yes.
I would first do numerical with minimum amount, maybe 2 theorems or 3 theorems at the
Okay.
most. But only when you get to the abstract, or even with at the end of numerical, you could hit a few that are really a bit more... this one, effectively, the first 3 questions are numerical.
Yes.
So it's not far from what they've been very familiar with in the early stages of the geometry. So I can console them and say, look at that, that was an exam question. 6 marks were just like the beginning part of our geometry. 4 marks are going to be a little bit more tough.
Yes.
But who cares? We've got 60%. We can maybe get more, but let's know we've got 60 in the bag.
I suppose you could liken it, carrying on with the color explanation, you could liken it to mixing paint. You have a problem there that's brown because it's got so many theorems muddled up into it. Isolate what the theorems are, so what colors
Correct,
have
that
gone
make
into
up that
it,
brown.
and then answer the questions.
Because I think that is the
by
problem
colour.
with children. I think they look at it and they get confounded by all these lines and all these letters instead of just focusing in. And that's why I like to teach it in picture form. Because if they're teaching it in picture form, they're looking for the pictures when they look at that.
Yes.
And like I mentioned 2 weeks ago, it would almost be interesting to take all the letters off that and say, okay, what can you see in this drawing?
Yes.
And I think in grade 11 you probably have more time to do that. but they would give them the experience of looking at it and drawing out what is the. Let's see who can find the most theorems we could have in this picture.
Almost like a Where's Wally type thing with your
I forgot my shirt again. I should have remembered my Where's Wally shirt.
Oh dear, have I brought it up more than once?
Now, you mentioned Where's Wally, and I mentioned I have a shirt. So here we have... I know I have a Where's Wally because one of the maths teachers at one of the schools I used to work at spotted me in it the other day and said, "Where's Wally?" So that's why I knew it was a Where's Wally shirt.
You were going to tell us about the last
that
question.
last one. It says prove V1 equal to PTS.
Yes.
So straight away my technique is V1 and PTS. I'd separate them like that.
Okay.
I say, okay, what can I find that's equal to V1 in this drawing? Well, V1, if I can see there, sort of out on a limb there. So it's not really connected at this moment in time. So let's go for PTS. PTS, and I'm just looking at my little drawing because my eyesight isn't one. I didn't manage to see that quite well just now. So PTS. Oh, my eyesight is really bad.
PTS.
Yeah, you can see that is an angle of a cyclic quad.
Okay.
So if I look at PTS, if I'm reading right, it would be that plus R1 and R2, I think. No, is it? No, it's not. Oops, I nearly made a huge mistake. So I haven't got that line drawn. Okay, I'm getting myself into a knot here. That's very bad. PTS. Okay, so PTS equal to V1. All right, so let's just look at it. What do we know? We know that P1 was equal to R2.
Okay.
In fact, that's so P1 equals R2, and R2 was equal to W. So what does that make WVPT?
You tell me.
Sorry, am I being mean and nasty here? Well, what's happened is we've managed to, through the earlier work we've done, and I've done a very bad drawing of it, let's call it VWTP, and that was extended. And we found this to be 40 degrees.
Okay.
And we found this to be 40 degrees. So that is the exterior angle of a cyclic quad.
Yes.
So that means there is a circle around these points. And I would encourage them to go to the drawing and put that circle in on the drawing in dots, so they know they put that circle in. It wasn't there before, though probably these circles would look like eggs. And then we would go now and say, right, well, what do I know about V1? And now it's easy, because V1, this one here, is equal to T1 for exactly the same reason. Because again, it's exterior. So what technique am I using here? I can't use the angles are equal. So what I'm doing is I'm saying, okay, if if we're proving A equal to B, I showed you last time that we could do A and B and find something they're both equal to, the same thing.
And then
conclusion, they're equal. But if that fails, you can say A plus something and B plus something equals some value, which is what we did. In this case, 180, or not 180, it's exterior angle, but we could have used 180. And then if these are equal, then by conclusion, those must be equal.
Okay.
That's the geometry logic we were taught in grade 8 in arithmetic.
Okay.
So it's another way to prove it. And we do use it in algebra. I mean, we will say x plus 2 equals 7, and x, let's make it y. Y plus 3 equals 8. Well, we can see that if we look at this, we bring this over, we'll get x equals 5 and y equals 5. So conclusion, x equals y.
Okay.
That's the logic we're using effectively here. So that last one was a bit mean.
So that would be level 4, maybe?
Yes, that would be level 3, definitely, maybe even level 4.
Okay.
It depends, how much they've been exposed to that kind of theorem.
Yes, Dylan.
Quick comment, maybe.
Mm-hmm.
How often, Leigh, is it the case that in a multi-part question like this, the first 3 answers are really leading you, prodding you, guiding you towards the big one?
Brilliant point.
Do examiners tend to always do that?
They scaffold. They call it scaffolding. And they scaffold the questions so that if you've done the earlier ones, you can get. And that brings another point into being. If for some reason, obviously this case it wouldn't work because it was numerical, but say they'd asked you to prove A equal to B in part 1, and then they asked you to prove B equal to C in part 2, and then they ask you D equal to E, but somehow it all connects in, then you may assume it, obviously you will lose the marks for the first one, and carry on to the second one and maybe get those marks. So that does happen. But yes, you're right, Dylan, they do scaffold it. And usually the theorem is connected. So probably the theorem you were asked to prove there would have been angles in the same segment, or maybe tan chord theorem. I would have asked tan chord, I think, if that one. Just as a hint to them, hang on, why did they ask me to prove that theory? It was for a reason, because I can use it in the next question. So that is very true. They do scaffold it, and it's because it makes it more accessible. So you can do the first 3, get your 60%, and the fourth one, okay, if you don't get finished, well, it's okay. 60% is not bad for geometry on a hardish question.
Cool.
So it's fine. Yeah, you're quite right. Thanks for that.
Okay.
Yep. I think that's most of what I wanted to say.
Well, it is definitely time to say goodbye.
Yes, as usual, yes. I've overtalked.
It's always a pleasure having you. Next week, we're talking about grade 12 statistics and counting and probability with our friend Robin, who's coming in.
I hate to tell you this.
Yes.
Robin's brother was a pupil of mine.
Well.
And she was at a school I taught at. She's excellent.
She is excellent. Yeah. That's why we have her. And Dylan has handed me a handwritten... I think this is the first time I've seen your handwriting, Dylan.
Yeah, it doesn't happen often.
No, but apparently we have a winner for airtime.
Oh, wonderful.
Yes. Well done, Etienne. It is Etienne.
Etienne?
Yes. Congratulations. We will be in contact with all the details. And join us next week when we talk about grade 12. Oh, remember, send your resources to competitions@digitalclassroom.co.za. I stumble over that every time.
It is quite a mouthful.
But maybe you have a cheat sheet that works really well and you want to share that with everyone, because it is actually quite difficult to find one online that has everything.
Especially one
for
that's
South
drawn
Africa.
beautifully.
Yes. So there's an idea. Use it, don't use it, but I'd use it.
It's always good to share your resources.
Yes. And thank you, Dylan, for all the magic behind the buttons. We'll see you again next week. Goodbye.
Bye.